we are going to start our lectures on advanced reaction engineering. So, today we will discuss about catalyst deactivations. So, in our previous class we already have discussed about the packed bed reactors. So, that packed bed reactors used for industrial reactions. So, their gas and solid phase reaction is there. So, their catalyst is the solid components that is put inside of a reactor, and then reactants will pass through that catalyst bed for the reactions. So, then reactant will pass through that bed at a particular temperature and pressure, then conversions will take place, that is the conventionals or that is the normal. So, for any reactions or catalytic activity. So, now once the reactions is going on for a particular reactors or reacting system, then catalyst deactivation part is coming. So, that is very important. So, when let us say any catalytic cracking reactions, let us say gas oil to other hydrocarbon formations, lower hydrocarbons, dry gas formations. In that case, it has been observed that coke formation is there when long chain hydrocarbons that is being cracked during catalytically or thermally. So, then coke formations is there, that coke could be deposited over the surface of the catalyst. So, when a catalyst take part in a reactions, in that catalyst there are so many active sites are available in the catalyst. So, that active sites take part in the reactions or for the bond breaking of the reactants to formation new bond formations, that is has a key role take part for that reactions or conversions. So, coke is deposited over the surface of the catalyst. So, then deactivations observed, and then rate of the reactions for that particular reactions gradually decrease with the time. So, therefore, that deactivations is play major role. So, how means what are the way, not only the coke formation, there are some other way also, means sometimes with the feed stream or the reactant streams, there are some poisonous molecules are available present in that means feed stream, that also sometimes gets trapped in the sites of the active sites, and therefore, that active sites is occupied by the particular poisonous molecules. So, then that active sites of the catalyst does not take part in the reactions. So, as a result, overall the rate, conversion, yield, selectivity, everything will be down for that system. So, today in the deactivations, here you can see this is the catalyst. So, we are maintaining temperature, and if we conduct the reaction in any packed bed reactor or solid phase reaction. So, here always what we expect, that activity of the catalyst, that is the remain constant throughout the reactions whenever we conduct the reactions. So, that is the means whenever we prepare a catalyst, the objective of the put any catalyst in a reaction system is that activity of the catalyst remain same or throughout. Let us say if we are conducting the reactions for 10 hours, 12 hours or 24 days, 30 days, 1 year, 2 years, throughout the years we should expect that catalyst gives activity, the activity or rate of the reaction should be the same. But in real case, it has been observed that in industrial or real operation, the catalyst lost its activity. So, here's here in the left hand side you can see, so how in a reaction. So, when the conversions, when time equals to 0 time, means at the beginning the conversion is very high. So, when as progress of the time is increased, means as the reactions we are conducting for longer period of times, the conversion gradually decrease, that is due to the deactivations of the catalyst. Okay. So, similarly, the activity, if we talk about that, so activity means when catalyst is going to deactivate or deactivation is there. So, then there is activity terms, means initially we expect that catalyst is highly active, and then activity that is actually expressed, our catalytic activity that is expressed in terms of rate at any times and rate at the beginning or t equals to 0, that is the ratio of 2 rates. Okay, that is the dimensionless parameter. So, activity that is ratio of 2 rates, means at any time rate divided by at the beginning. So, at the beginning, so when the fresh catalyst we have, it has highly active. So, then that is the maximum activity or the performance of a catalyst can give. Okay. So, then this is the activity. If we means want to look the performance of a catalyst in terms of activity, then it is observed that with the increasing time the activity at the beginning it was very high, and then with progress of the reactions it gradually decrease. So, at any times after a certain period of time, so maybe if we operate the reactors very long times, then the activity would be 0, almost catalyst deactivates completely, that do not take part in the reaction. Then again we have to change the catalyst and we have to replace the new catalyst in the reactors. So, here the reactions activity and reactions rate law that we have written here. This is the activity in terms of the ratio of the rate. So, this we are writing this way, means just writing the rate at any times in terms of activity, and this is the rate of the reactions when at the beginning or fresh catalyst or time t equals to 0. Okay. So, it is the product of activity and rate. Catalyst does not deactivate during the reactions, then A t would be a 1. So, for the most of the cases when catalyst does not deactivate, then it is or activity is 1. So, then rate at any times and at the beginnings remain the constant, that is the normal cases, but when the catalyst deactivation is there, then this activity terms is very important, that you have to include in the rate equations or rate terms, whatever the way we are expressing the rate of a reaction, then that part will come. Okay. So, then usually rate we express in terms of reactions rate constant and concentrations of the reactant that is take part in the reaction, that in may be component A or component B in terms of concentration, that way we usually write any rate. So, this part is coming activity terms. So, activity means when it is coming in the rate equation. So, then catalyst means for the reactions there is a rate equations, and when catalyst is going to deactivate, that deactivations also with increasing time. So, that may be means there is a decay rate law also, we can say that we can means this is the reactions rate law for catalytic activity for the reactions. Similarly, catalyst when going to deactivate, that deactivation may be many reasons, that we will discuss step by steps, means what are the various way or types of catalyst deactivations are there, so that we will discuss. So, here catalyst deactivations rate we can write in this way, means R d equal to rate of deactivations of that particular system or catalyst minus d A by d t into P activity terms some functions deactivation constant, similar like rate constant, this is the rate constant or specific reaction rate. Similarly, for reactions decay or deactivation is there, that rate also you need to know. For that deactivation rate constants we are expressing K d as a function of temperature and some concentrations also, that means reactants species are there depending upon, means let us say some poisons are there inside of that feed streams, or reactants concentration are there, means some reactants, here the reactions you can say these are the reactants that also take part in the reactions, and that also would come in the decay catalyst catalyst decay rate law. Okay. So, this decay or activity or catalyst deactivation. So, this is function of activity that we can express if it is first order, then a to the power n, if it is second order a to the power 2. So, it may be first order, second order, 0 order like normal reactions. Catalyst deactivations also may be first order, second order or second order or fractional order of catalyst deactivations order, we can write that way. Okay. Similarly, as we do for the reactions, similarly catalyst deactivations or catalyst decay rate law, there also the activity we can express this way. Okay. So, this is the rate law we discussed. So, now there are various type of catalyst deactivations I said. So, number 1, that is the due to the sintering or aging. Okay. So, number 2 is the fouling or coking, and number 3 is the poisoning. These are the normal means 3 different type of catalyst deactivations when any reactions cracking or any reactions we are conduct any normal reactions. So, then these are the things usually observed for that deactivations reasons. So, what are the reasons? So, now one by one that we will discuss. So, means first one, that sintering or aging of catalyst activity, how that is and how that is affect the overall rate of the reactions. And let us say the sintering or aging of the catalyst means the catalyst activity. Let us say suppose you have a solid catalyst, I said that this is a catalyst, we have a catalyst. So, in that catalyst we said there are so many micropore, mesopore, macropores are available. Inside of the pores you can see that there are active sites are available. Okay. So, this is the pore mouth. So, here A and B, that is the reactant that will enter and take part in the reactions. So, conversions or for that reaction that will occur. So, here in that catalyst it has a particular surface area or specific surface area or BT surface area of this catalyst. So, when we conduct any reactions at, let us say, at high temperatures, so what is happened? So, usually at, let us say, if we conduct these reactions, let us say 500 degree centigrade, and that is a particular temperature where that particular catalyst does not affect so much. So, if the reaction is maybe exothermic, or maybe if we conduct the reactions at, let us say 700 degree centigrade or 800 degree, same reactions if we conduct some higher temperature, or maybe some heat evolution is there during the reaction. So, somehow the catalyst surface area or catalyst agglomerations or sintering, means here the active sites is there, surface area will be downs, or loss of active surface area, or maybe catalyst crystal agglomerations. Here the catalyst sites are available, that sites may be small nano range is there. So, if high temperature is there, so it forms a larger particles agglomerations. So, this is the changes, means when agglomerations is there. So, then here you can see at the beginnings very small catalyst active site distributed over the support of the catalyst, but after T time large particles formations is there. So, this is called agglomeration. So, therefore, number of active sites initially the numbers was there. So, after a certain period of time that decrease. So, therefore, overall catalytic activity will decrease, that is the one of the reasons. And another one is the closing or narrowing the pore inside of the catalyst. I said that catalyst has so many pores, that micropores, mesopores, that may be blocks. So, here initially the pore was pore diameter, let us say this. So, after a certain period of times due to the agglomerations or narrowing the pore size, so it is decreased. So, then as a result what would happen if it is blocked sometimes. So, then what would happen that reactant molecules does not take part in the reactions with the active sites of the catalyst. So, then overall activity will decrease. Okay. So, here one example is given for, let us say, the catalyst deactivation, that is the second order decay we can say. So, here rate of decay, that is R d, we can write K d means and A square, that is equals to minus dA by dt. So, here K d is the decay rate constant and A is that activity. So, that we are writing, we are rearranging and then integrating with respect to the A equals to 1 when t equals to 0, and when t equals to t, A equals to A is the A, that is the activity at any time. Okay. So, initially always that should be 1, and then A may be, that is any fractional numbers, that may be 0.8, 0.6, 0.7 like that. So, if we integrate, rearrange and then integrate it, so we will get this. Okay. After integration with respect to this boundary conditions, if we integrate this, so after rearranging we will get this, it is the activity equals to 1 by 1 plus K d into T. Here K d is the deactivations rate constant. Okay. So, deactivation constants K d, and here is the time. So, at if we know this value and if we put it here in these equations, and at any time, so what would be the activity? Let us say if a time span of 60 minutes, if you want to know the catalytic activity at different times, means 0 minute to 60 minutes. So, then just we put time at particular times, maybe 30 minutes, 45 minutes, what would be the activity, that easily we can measure, means by for a particular deactivations process. So, we can find out. So, here let us say the rate law is, we can write for a catalytic activity, the at the beginning of the definitions we said that this is the rate at any times, this is the activity, and this is the rate constant, and this is the concentration. So, that way we can write. So, here this A t we can substitute, here this A t we have obtains, that we are putting inside of this rate law. So, here this is coming this. Okay. So, now we can write or express the concentrations in terms of this. Okay. So, here C A equals to N A by V, N A equals to N A naught into 1 minus x, okay, but and V divided by V. So, this we are writing this way. Okay. So, now let us say we have a batch reactors, the if we conduct any reactions in a batch reactor. So, batch reactors means solid and gas phase reactions if you are conducting, and then there is a catalyst deactivation is there. So, the design equation for a batch reactors we can write dNA by dt equals to Ra into V. So, these equations we are expressing since, so this is the design equation for batch reactors when we conducting a solid and gas reactions. In that case the design equations we can express in this way. Okay. So, here instead of Ra we are writing minus Ra primes, and here instead of volumes we are putting weight of the catalyst. So, these design equations we can means this is the design equation for the batch reactors, and red equations we have obtained this. Here we have put it the deactivations part also 1 upon 1 plus k d into T. So, now this we are substituting in this design equations, or for the batch reactor for the case of the solid and gas phase reactions, if we consider W amount of the catalyst and the rate of the reactions is minus Ra prime. Okay. So, now after substitutions we are getting this, okay, in the right hand side. So, then we are rearranging at taking k equals to k prime by into W by V if we take, and then integrating with respect to t when t equals to 0, then x equal to 0, when t equal to t x equal to x. So, with this boundary conditions if we integrate this after rearranging, this is dx by dt is there. So, x limit is 0 to x, t limit is 0 to t. Okay. So, with that boundary conditions if we integrate these equations, so then finally we get this. This is the second order catalyst decay, second order catalyst decay rate law for first order reactions for in a batch reactors. So, here reactions let us say A plus B going to C plus D, here red equations, this is the reactions rate. So, the reactions rate we have first order reactions we have considered n equals to 1 for in a batch reactors that we have considered, but the catalyst deactivation that was the second order that we have taken here, catalyst decay rate law second order we have considered for the decay rate law, catalyst deactivating in the second order, the order is the second order, and reactions that is the first order we have taken, so n equals to 1, and that reactions was conducted in a batch reactor. So, that way we are expressing. So, this is actually means combinations of catalyst for the reactions as well as catalyst deactivations, both are there when this is the combined or final equations that we are generating. Okay. So, here you can see K and Kd, small k is the reactions rate constants, that is reactions rate constant, and for deactivation catalyst deactivation rate constant is this. Okay. So, reaction rate constant for a particular reactions if you know, catalyst deactivation rate constant if you know, then if we put here and then at different times means if we conduct the reactions under that conditions. So, then the conversions how will vary with time. So, that we can easily evaluate the conversion as a function of times we can find out. So, if we know the two things, reactions rate constant for a particular reactions that we are want to know the conversions at a particular time. So, when that catalyst deactivations is there. So, with increasing times or decreasing times, what would be the conversions at that particular times, that using these equations we easily can calculate or we can find out. Okay. Aging or sintering. So, that part we discussed. Now, catalyst due to the coking or fouling. So, this is another type of deactivations, means I said if any this type of reactions is there, coke formation is there, that would be deposited over the surface of the catalyst. So, this is the active sites of the catalyst. So, here coke would be deposited. So, then active sites would be blocked. So, then that would not take part in the reactions. So, then that is another type coking or coke. So, how much coke formation is there? So, that also we can calculate if we have any equations, means correlations with for a particular system. So, then we can use that correlation to find out how much weight or weight percentage of coke is deposited within a stipulated time. So, that we can easily find out also. Okay. So, that things we will discuss. So, I said that catalyst deactivation due to the fouling or coking. So, here this is the catalyst pores or catalysts these are the catalyst active sites inside of the pores, that is I said. So, this catalyst, if we look into this way, so these are the active sites, there are so many pores, these are the active sites that take part, means that is the take part in the reactions for a particular reactions. This is the active sites of the catalyst. So, initially t equal to, when time t equal to 0, fresh catalyst we have used, there is nothing is there. So, activity would be very high. Okay. So, then reactions rate also would be very high, but when coke deposited, these reactions we are taking place, means conducting in presence of this catalyst, then this type of coke formations would be there, that would be deposited over the surface, that may blocks that surface sides or pores, then catalyst deactivations will observe. Okay. So, this type of study has been done, and here few correlations, means concentration of the carbons, concentration, I said the how much percentage of carbon or concentration is there, that carbon concentration we can easily find out. Here A and A, that are the fouling parameters. So, that trial and error we have to find out those things for a particular system. So, once we know A and N value for this particular systems, so with time concentration of the coke, that easily we can find out. Okay. If A and N are known for a particular specified system, so then let us say A equals to 1.2 and N equals to let us say 0.5, that is known for a specified system. So, then Cc equals to A 1.2 t to the power 0.5, that way we can write these equations. Then with time, if you know 0 to let us say 60 minute times, if you want to find out concentration of the coke deposited over there. So, then with time we can find. Okay. So, this is the way we can find out, or these correlations we can find out, or we can use for our systems when there is coking or fouling is there. Similarly, another correlations is also available, percentage coke deposited, that is directly with the time. So, the other parameter or constant here, A you can say 0.4 and N equals to 0.5 in this particular cases. So, here percentage coke in the form of percentage or in terms of concentrations, we can either way we can express. Okay. So, there are some others means correlations also are available depending upon that amount of coke that is deposited. So, when a catalyst surface is coke deposited, so we can heat it up that or regenerate that catalyst by passing air or oxygens at a particular temperature. So, then coke would be oxidized in presence of oxygen. So, it would form CO2. So, by that way you can remove that deposited coke over the surface of the catalyst. Therefore, the suppose you have a catalyst that is deposited by coke. So, if we want to remove the concentration of the coke, so then how long oxygens or other things we have to pass over the surface of the catalyst at the particular time. So, if that catalyst deactivations we can express in terms of burning of coke or carbons that is deposited over the surface over the catalyst surface of the catalyst. So, that is case 1. So, these are the commonly used forms that we can use, or we should know, that is the activity in terms of time. Okay. So, here k prime at m, that is the constant or parameter for this equation. So, here this activity also in terms of the activity we can write this, and then in terms of coke, the activity coke concentrations, and this is some constant, and this is p is the some parameters also for this particular equation. If kck and p is known for that particular specified system, these correlations also we can use to find out the how means the performance of the catalyst, means the activity of the catalyst that is changing with the time. Okay. So, that way also amount of coke deposited that we can find out. Okay. If we know the amount of coke, then activity of that means catalyst deactivation process due to the coke deposition, that we can easily find out. Okay. So, next third one is the catalyst deactivations by poisons. I said suppose we have a feed stream gas oil like that. So, with that when reactant is passing in the reactor. So, we have a reactor. So, here we have a catalyst beds, here we are passing reactants for the conversion at a particular temperature and pressure. So, when reactant is passing, with that some other components maybe impurities, this is sulfur, NO, H2S, CO, that may be impurity present in the feed stream. Okay. So, 100% pure compound is not sometimes available, means for the industrial operation or industrial study. So, some impurity may be there, that impurity sometimes it is not possible to separate out all of them. So, sometimes some fractions may be present there, that also pass with that feed stream or reactant streams, that is coming to the inside of the reactors, that may be deposited over the surface of the active sites of the catalyst. As a result, that catalyst active sites would be blocked by that poisons molecules. So, then that active site would not take part in the reactions, therefore, the overall performance of the catalyst will deactivate. So, these are the molecules sometimes is called poisons. Okay. So, that poison molecules irreversibly chemisms on the active sites of the catalyst, and therefore, reducing the number of total sites available for the main reactions. Okay. The poison molecules may be product, impurities, or that is present in that streams, or maybe reactants, sometimes also some reactants may be poisons, acts as a poison. So, here so you can see this is our catalyst. So, here A is the reactant, B, C, these are the products. So, A reactant, that is this is the active site, here it is absorbed for the reactions. At the same time the product formation is there, B may be adsorbs over the surface of the catalyst active sites, and then it would be dissolved, then we will get the products. Similarly, at the same time that poison molecules also, these are the poison molecules that may be take means absorbs at the beginnings, one poisons molecules absorbs, after a certain period of times when increasing times number of poisons molecules, that is get adsorbs over the surface of the sites more. So, similarly, after a long period of times, if we run the systems or the catalyst inside of the reactors for a times longer time span, let us say 1 day, 2 day, 3 day, 5 days, 30 days. So, then after a long period of times we can see so many poisons molecules may be occupied the active sites. After a certain period of times, maybe the performance of catalyst will be decreased. Okay. So, that is due to the poisonous molecules present inside of the reactors. So, this deactivations of the poisons. So, here the main reaction is this, let us say this is your main reaction, means reactant A participated in the reactions and it is going to formation of B. For that may be a reversible reactions, so maybe possibilities there, multiple steps. So, we are here considering by non-elementary number of, means by proceeding adsorptions, surface reactions and desorptions of component B. So, like that way product B formations is there. So, these details mechanisms we will discuss later. So, in our another lecture. So, now we are not going to discuss, our main purpose is to discuss on the deactivations part. Therefore, the main reactions, if you know this is the rate law. So, rate law we can write rate of reactions activity, and this is the rate the rate of the reactions that is coming. So, minus R A equals to A T into minus R A. Okay. So, this is the rate equation, this is at time t and this is at t equals to 0. Okay. So, that we have discussed just previous slides. So, here the rate equation for this particular reactions we are substituting here activity terms, and this if A equals to 1, so then initial and finals rates would be the same, there is no changes, but here we are discussing about the deactivations, means the catalytic activity with the progress of the reactions may be a decrease, that may be like that. So, it is decreased. So, therefore, that part we also include in the rate equations. Now, due to the poisons, so I said some poison molecule is also there, that is expressing in terms of P, the S is the active sites of the catalyst that is absorbed, I said already. So, for that the decay rate law we can write this way. Okay. So, here K d prime is the decay rate constant, and this is the concentration of the poisons, and this is the concentrations of active sites that is present or activity in terms em and q, that are the some parameters em and q respective for this particular system. So, that we can easily find out with the kd prime m and q, that also we can find out. So, by trial and error. Okay. So, the removal of poisons, that is CPS is the concentration of the poison sites, Cp is the concentration of the poisons, and Ct is the Ct0 is the total site presence. Total site means in the catalyst surface the total sites at the beginning is present, that is we are expressing Ct0 total sites available, and poisons molecules occupies that amount. So, the number of active sites unpoisoned or available, that is Ct0 minus Cps. So, that is number of sites available for the reactions purpose. Okay. So, then rate of removal of poisons, that we can write Kd deactivation rate constant, Ct0 minus Cps, that is the number of sites available or unpoisoned. Okay. And with the concentration of poison gas, that is in the form of gas, it is available inside of the system. So, here you can see here total number of active sites, and this is concentration of the poisons, component E is also there. So, this is the active sites, this is the concentration of the number of unpoisoned sites available, and this is the concentration of the poisons molecules that is present inside of that systems. If we write the rate equations for rate of removal of poisons, we can write this way. So, if it is means the same thing, so here this RPS, that we can write in terms of dCPS by dt equals to RPS equals to this right hand side remain the same. So, now here's left hand side and right hand sides, we are these terms and these terms we are dividing by CT0 we are dividing both side by CT0. So, then these terms would become this F equals to Cps divided by Ct0, and in the right hand side Kd is there, Ct0 that would be Ct by Ct0 equals to 1, and Cps by Ct0, that is F, that is the fraction of total size that have been poisoned. Cps is the concentration of the poisons, and this is the total sites, this is the concentration of the poison sites by total site, that is the fraction of the total sites that have been poisoned. So, this 1 minus F into Cp, that is the number of sites that is available, 1 minus F, that is the number of sites available for adsorptions, means F is the fraction that has been poisons molecules, the active site that is poisoned, that is covered by the poisons molecules, and 1 minus F, that is the fractional sites that is available for reactions. Okay. So, these equations we can write this way. So, here 1 minus F equals to 80. So, if you differentiate this, so we will get minus dF equals to d80. So, if you substitute this here, then these equations will come this, here it is the activity. So, minus d80 by dt equals to 80 Kd into Cp. So, this equations it is coming in terms of activity, deactivation rate constant, and concentration of poisons. Okay. So, these equations we can use, or this is the rate equations for deactivations. Okay. So, if we know the concentration of the poisons and At the activity of the catalyst, that activity, that terms we have to put for the deactivations purpose. So, it may be deactivation rate constant also we have to put. So, here we have discussed in case of first order or second order this type of equations we have derived this. So, this depending upon deactivations or At, that is here we have considered second order decay rate dot, that may be first order or any other order, that part we can put over there, and by that way we can express the rate equations for deactivations due to the poisons or poisons molecules that is present in the feed streams, that deactivation rate law we can write this way. Okay. So, these are the things are useful. So, whenever we are going to study any catalyst deactivations for a catalytic systems, that is very useful. So, okay. So, now we have discussed 3 different type of deactivations process when a catalytic crackings or catalyst going to deactivate. So, various way catalyst deactivations are there. So, how we can express them with the rate equations for the reactions. So, that we have discussed. Okay. So, today is up to this. Thank you. So, we will discuss other things in our next class. Okay. So, okay, thank you.